Alright, so good morning. As you can tell, I don't really have a voice, so I hope this goes okay. I'll go as long as I can and have to pause if I need to. So today we're going to start chapter 3. Before we get going, I wanted to just make sure we have a little chit chat about school. We're getting down to almost a semester. This is kind of the last stretch before our semester test comes up. We need to make sure that we are doing everything we can to not only understand all the concepts, but make sure we're passing. I have been given a lot of dirty looks lately based on grades, and a lot of it is based on you guys, whether or not you want to do the work or not. So if you guys are the ones not wanting to work, then you're going to get the grade that suffers for it. That's how it's going to be, and that's just how it is. So, okay, moving forward, let's make sure we're doing as much as we can to continue understanding the concept. Okay, so first things first, we have the book's definition of an extrema. So I'm going to move this, you write it down, and then we'll talk about it. Remember, if you need to pause, pause. Okay, let f be a function. Remember, we always let f be functions. Let f be a function defined on some interval I, containing a point C. First thing that happens when we do that is, if I plug in this value of C into my function, there's somewhere a minimum where that value is the smallest y value that I will get compared to all other x values. And this is supposed to have an equal line. I don't know why that doesn't have an equal to line. Gotta fix that. Oh, I don't want you purple. And then the next one is the opposite. There exists somewhere some maximum where that y value is the biggest y value possible that you will see on your graph. And I'm going to fix that because that looks really bad. Okay. So that's what that first part is saying. That someplace on my graphs, on my interval being this x to this x, there's some y value on there, no matter what the graph looks like, that there is a maximum point and a minimum point. Okay, so what does that mean? Well, let's talk about that. Let's say we had the graph. I'm going to switch colors here real quick. I had a dot over here, and I had a point somewhere over here on the on my axis. So I have some points I want to talk about. If you notice, I know I kind of drew it badly, but this, I'm going to fix that. Hold on, I know, pause, I'm sorry. It's not the easiest drawing on these computers sometimes. I know a couple different points here, but same kind of idea. Notice how these dots are closed, they're solid, they're filled in, that means they exist. So that means that this point down here is going to be my minimum. And then this point up here would be my maximum because it's the smallest and the biggest y values that I see on my graph. However, on this second one, we have some open dots. So on this one, I only have a minimum because this point here does not exist in my graph. We don't actually touch it. So this one's actually not a maximum. Oh, excuse me. So it has to be in that interval. So on the second graph here, this spot, this hole, is not a maximum. The one right next to it would be a maximum, but this part is actually not a max because it doesn't exist. Okay. Next theorem. You write that down. I'll give you a couple seconds. I need to go blow my nose. Okay, so what that's saying is, if it's a closed interval, well, closed intervals mean something that looks like this. If you're on a closed interval from A to B, then f has both a minimum and a maximum on the interval. So, over here I have this little drawing that you're going to need to go ahead and do it. Scroll down a second. So what this is saying is, it's hard to tell, but in this case I would let B be my maximum. And this point here in the middle be my minimum. Now these are a closed interval, so that's the example that we just saw in the first one. So if I go back a second, this first picture here is a closed interval. This one is an open interval. That means those points don't exist in the graph. Okay, that being said, we have some more stuff we're going to talk about. I'm going to give you one at a time on this one. So first thing, talking about relative extrema. If there's an open interval containing some value c, on which f of c is a maximum, then f of c is called a relative maximum. Likewise, if there's an open interval containing c where c is a minimum, then it's called a relative minimum. So what does that look like? Well, say I have, I'm going to switch to red. Say I have some points over here, and I have a point down here. And then I just kind of connect them. On this open interval, because it doesn't end, because if I scroll down a second, you can see how these are not ending. There's not a specific start and end. It goes from negative infinity to positive infinity. So because these do not end, there's no endpoints. There's no, oh, here's my start, here's my stop. This point up here would be considered my relative maximum. And this point down here would be my relative minimum. Now, does that mean you can have only one relative max and min? Or does that mean that you could have several? You could really have several. Say I had sorry, it's really hard to draw these sometimes. So I had a graph that looked kind of like this. Let's talk about all these different points. Well, this first point here, it's kind of hard to tell, but that one would have been a relative max because it's still a high part, and it's based on the area. So if I'm looking at that little spot, that's the highest point in that area. Now this point is not anything. It doesn't flip, it doesn't do anything, it's just continuing on my line, so this is nothing. This point is supposed to be a relative minimum, so just kind of fixtures if it doesn't look like it. It's supposed to be a relative minimum. Then this guy would be a relative max. Again, this point here, this next one, is going in with it's just still in line. It's not either, it's not the bottom or the top of anything, so this one is nothing or none. This guy, you can guess it would be a relative min. The next guy is going to be a relative max. And this last one, again, he's just like these other two. He's just continuing on. There's no divot, there's no hill, there's no valley. So he's just nothing. So that being said, go ahead and graph this next one. And we're going to talk about it together. About what you notice at all these individual points. I'm going to type this part up because it's getting difficult for some reason to write on my computer today. Alright. What do you notice about A? Minimum, maximum, nothing. Well, he's supposed to be a relative minimum again. Doing these as best as we can, plotting on a computer is not the easiest thing. B should be a relative maximum. C, you guessed it, relative minimum. D would be, in that case, another relative maximum. I don't know why this isn't letting me type here. And then E, again, this would be nothing, none, whatever, because it's not, again, a hill or a valley. There's nothing going on there. So, I'm going to pick a different color because I want to point this out. I'm going to write it through my graph because I don't want to move anything. What do you notice at all extreme? What do you notice at all of these points of extrema are all the extrema points? Specifically, what do you notice about their slope? Well, at all hills and valleys, my slope is nothing. My slope is going to be 0. But we've been working on something for the past, what, 2 months now? That talks about slope. What is a slope? What's another word for it? What's the math or the calculus behind what we've been doing? What's that calculus word that we've been doing for the past 2 months? Derivative. Remember, derivatives are slopes. So what we're going to be looking for is when my derivative is equal to 0. Since all these extremal points, their slopes are 0. Derivatives are slopes, so therefore my derivatives are going to be set to equal to 0. So that's what's going to lead us into this next part. So what we're going to do with this next one is we're going to find the value of the extrema based on this function at the point 0, 0. So we're going to figure out what that slope is. And we're going to care about this in like 3 more sections. We'll really put this into practice, but these next couple sections are getting us there, getting us ready, so we don't just jump right into it. We're not diving straight into the deep end. We're kind of waiting in there. So what we need to do first is we're going to take the derivative of this guy. And we should know that derivatives, when I see a... wow, I can't talk. When I see a fraction, I should know that derivatives of fractions are going to be quotient rule. So quotient rule is low, or whatever's on the bottom. So I have 2x squared plus 8 times the derivative of the top, which is going to be 4x. Minus the top function, so 2x squared, times the derivative of the bottom, which will give me 4x. All over the bottom thing squared. Alright, let's multiply stuff through. 2 times 4 gives me 8, so then I have 8x cubed. 8 times 4 gives me 32. And then my 2 times my 4 gives me an 8, but we have to distribute that negative sign, so it's going to be negative 8x cubed. All over my bottom squared. My 8x cubes on top cancel each other out, so I'm just left with 32x over 2x. Ooh, let's fix that too. 2x squared plus 8 quantity squared. So now what we want to do, hold on, let me extend this page for a second, is we want to see what happens when x is 0. So let's plug in 0. So I have 32, 0 over 2 times 0 squared plus 8 quantity squared, which would give me 0 over 64, which gives me 0. So we should know that that's extreme and we should get 0. But again, it's leading us into what's going to be going on next for these next couple sections. So I know blah blah should be 0, but because I can see it here at this point, 0, 0, it's going to be 0. But I want to talk about mathematically because you're going to have to do this in your homework today. Okay, so there's your homework. Get going.